Hello, welcome to GeoAI tutorial number 11. In this video, I'm going to show you how to train deep learning models for object detection from satellite or aerial imagery, just with couple lines of code using the GeoAI package. So specifically in this tutorial, I'm going to show you how to train a building detection model. Before we get into the demo, I want to show you the result. So this is the map showing you the aerial imagery and with building footprint that detected using the model that we're going to train later. And you will also regularize the building footprint. So this look really nice. Of course, it is not going to be perfect. There might be some missing the buildings, or maybe the shape might not be exactly the same as the buildings. It's normal. You can always fine tune the model a little bit more to get a better result. But as you can see, it looks pretty nice. And it only takes less than a minute to train a pre-trained model. Then you can get a result. So all we need is just imagery and also some labels. It can be a vector dataset or it can be a raster dataset. So only two datasets. And then the GeoAI package will take care of all the heavy lifting to create the image chips for doing the training, and also going to do the inference on your imagery. So you can run inference on a large imagery. You don't have to worry about creating image chips and then merge all the results together. So let me show you step by step how to get it. First, you need to go to the GeoAI website. The link is in the video description below. And then go to examples, scroll down to find train object detection model. So click the URL. And then from here, you can either run this notebook using Google Colab. So right click to open this one in Google Colab. Make sure you switch to the GPU. So change the runtime type and then change to T4 GPU. Click save. Then you can run through the notebook step by step. Or you can install it on your local computer if you have GPU. So upper right corner here, download this one to a computer, and then you need to set it up, install the packages on your computer. If you want to learn more about how to do the installation, check out the video, the description below about the YouTube playlist. So I've created a lot of tutorials from installing the packages, downloading the data, and then use that for detection. But today we're going to show you how to train the model, train your own model, so you don't necessarily have to use other people's model. You can train your own models using some other pre-trained models, and then just take you a couple minutes, you can have your customized building detection model. So let me show you step by step how to do that. I'm going to go to the very beginning here. So the first step is to import the library. I can just import the GeoAI package. And we're going to download some sample data. So in this tutorial, we need 3 data sets. The first one is the training data set. So it's an imagery. It can be a satellite imagery. It can be aerial imagery or even drone imagery. And the other one is the label. So basically the building. So in this case, we have the aerial imagery and have the building covering the imagery. Also, we're going to have another one called test imagery. So basically, after you create the training model, you might want to test that on a different data set. Let's run this one, and these 3 lines of code just going to download the data set. Once you have the data set, now we can visualize and see what the data looks like. So just call the GeoAI.view vector interactive, then just passing the vector data set we have. We are going to use the aerial imagery as the base map. So just one line of code, you can visualize the data easily using GeoAI. So this is what it looks like. And like I said, it can be any other data set that you have. All you need is just a raster imagery and also a vector data set. So the raster imagery, right now, this one is from the USDA NAM imagery, National Agricultural Imagery Program. So it's, for example, this is 60 centimeter resolution. Up right here, you should be able to, there's a layer control here. You can turn the layer on or off. So this is an area covering Washington, a residential area in Washington state. And so the building comes from the Overture Maps dataset. If you're interested in where to download the dataset, you can look at tutorial number 2. I show you how to download dataset for any location around the US and also download the building footprint dataset. So once you have the dataset, now we can use it for doing training. So you don't need to have a huge dataset. All you need is just imagery and a vector dataset. GeoAI will create a train image chips for you later. So this will be the training data. The other one we want to look at is the testing data. So this is another imagery, kind of a around the similar location here is actually at the bottom of this imagery. They are the two imagery, and this is the different imagery. So we're not using this one for training. We're just downloading the imagery, and we're going to use this one for doing testing. So once we have the model, how can we test if it performs well or not? Okay, so now we have the data set ready. So the next step is to create training data, and this is a step that you only need one line of code. Traditionally, you have to worry about, okay, how do I create the image chips? How do I make sure that they overlap? And also, how do you convert the vector data set to raster? And then you need to create the corresponding labels. It takes a lot of time, so GMap makes it really easy for you. All you need is just one line of code. So GeoAI.export GeoTIFF tiles, and then you can pass in your data set. So your GeoTIFF, so this is the one that we have downloaded, is the area imagery. Also specify where you want to output to the directory. So I'm going to create an output directory. Also the in-class data. So basically this is the label. In this case, it's the building footprint, right? So it's a vector data set, it's a GeoJSON, or it can be Shapefile or any other vector data set supported by GeoPandas. Then you can specify the tile size. So basically how big is the image tile, because when we need to do the deep learning to do the training, we need to subdivide it into smaller pieces. And you need to make sure that the imagery has the corresponding label. The stripe means is the overlap. So we are creating 512 by 512. So we basically have the sliding window, okay, from the left to the right, from the top to the bottom. You need to make sure that they have some overlap. Otherwise, if a building happens to be along the edges of two images, sometimes they might be missed because the model might not be to detect half the building. And so if you make sure they have overlap, then in that case, you want to have complete buildings. You might need to change this one, adjust the number depending on the object you want to detect. If you're detecting a large object, you might want to increase the tile size and also the stripe size. If you're detecting small object, I mean, in general, this is probably the default parameter is fine. Also, there's a buffer radius, whether you want to later once we create, whether we want to have a buffer around the object or not. You can just set it as default. Then take a look. So now it's creating the image chips. It's going to basically sliding through from the left to the right, from top to bottom. And at the end, it's going to show you how many tiles we have. So you can also look at the basic information. This is the EPSG 26911. How many columns, X and Y. So how many columns, how many rows. The spatial resolution. So this is 0.6 meter. And this is what the USDA name imagery provide. Also, keep in mind, we have 4 bands. So we have RGB and also near infrared. So in this model, we're going to use four bands for doing the training. So most of the object detection models uses 3 bands, but you can use any remote sensing imagery has more than 3 bands. So this one has 4. You can also use the same procedure to train other satellite images. For example, Landsat, Sentinel. They can have 6, they can have 10, it doesn't matter. So all you need is just to later specify how many channels you want to use for doing the training. And after that, you should be able to see how many, for example, how many tiles in total, 36, okay? And for each tile, they're going to have some buildings. Some of the tiles might have buildings, some might have not. And they are all output to the output directory. So if you go to your Jupyter notebook here and click this one, output, inside here should be able to find the image directory. So all the tiles have been created from tile 0 all the way to scroll down to the bottom. So it'll be 35. So these are all the tiles, and they also have corresponding labels. So basically for each imagery, we have the corresponding raster labels. So that later we can use it to train the deep learning models. If you want, you can open this data in or load it in the Jupyter notebook. They are all georeferenced, so they are still GeoTIFF. They are not just JPEG or PNG. You can open this one in QGIS or desktop GIS. You will be able to see the labels align very well with the imagery. Also, it has an annotation. So this is just XML. So basically, for every image tile, it's going to figure out basically the bounding box for each object. We don't really need this one, but just it's some kind of format that's required by other deep learning models if you want to do the training. In this tutorial, we're not going to use that, but you will find it in the annotations output directory. Okay, so Now we have the training data ready. So the next step is to train the deep learning models. And this is a step that is usually very time consuming because not everyone is a deep learning expert. You don't necessarily have the skills to build the architectures for the deep learning model. And it's very time consuming. Right now, I've basically simplified the steps. So you only need just one line of code. Train mass RCNN model. So this is an object detection model using the mass RCNN architecture. You don't need to know the technical details. All you need is that, okay, it's a model and we have some image chips. We have some corresponding labels. We want to use this one to train the model. And you can also tell how many spectral bands you're going to use. Like I said, in this case, we have 4. You need to change this number depends on the number of channels that your imagery have. And also, do you want to use the pre-train or not? In this case, we select true because we can use the pre-train weight from the mass RCNN model. It's going to be so much faster because it has been trained on a lot of images. But we are actually only fine-tuning the model for our use case. Also specify the batch size is how many images you want to fit into the model at once. So we have basically 4 images at once. The number of epochs you want to train. So we can select 10. You can increase the number if you want to be have better accuracy. You can increase that. And also the learning rate is basically the rate we use to adjust the hyper parameters. You can use this one, the default settings. Also the validation split means how much you want to use for training and how much you want to use for validation. So in this case, 0.2 means 80% for training, 20% for validation. You can press Shift on your keyboard to learn or to get to see all the help documentation. And if you are interested in seeing the source code behind, you can go to the GeoAI website and then click the train module. On the right here, you should be able to find train mass RCNN model. Click this one. And from here, you can scroll down. You can look at the source code. Although right now we're using just one line of code, but you can scroll down. This is hundreds lines of code to basically simplify the process. And the good thing is about it's you can also extend it to do other object detection. It doesn't have to be building. It can be pretty much anything else. As long as you have the imagery, you have the label, then you should be able to use that. So with this, we are ready to train the model. So just run it. And it's going to automatically use GPU. You have GPU. You will also find out how many image files that we have, and also how many labels. So in this case, we have 36. Then you're gonna start training the model. So starting from epoch 1 all the way to 10. Also, you're gonna print out some numbers, the training loss, the validation loss, and also the IOU. And you can quickly see the IOU increase. This is a good sign. So IOU range from 0 to 1, so you want the higher the better. IOU basically means intersection over union. That means is your detected object divided by the union. So basically your detected object and also the ground truth. So the more overlap they have, the better. And it's done. So we only train 10 epochs and we use the pre-trained weights from the original mass RCNN model. And it's not from any remote sensing model. So this is from the total vision mass RCNN model with the pre-trained weight. And we only train like 10 epochs. It takes less than 1 minute. Now we have the model. So it's going to save you model save to output models. And if you want, you can go to here, click the models. You should be able to find, for example, in this case, you have all the model here, base, the base model. So what you want is this one. And also you're going to show you, for example, checkpoint epoch 10. So these are all the same, right? So the base model, the final model, we can usually just use the base model to do the reference, okay? And that's it. So the training is done. Now we can run the reference. And we are going to use this, where is it? Oh, this first you need to specify the output. So for the reference, it's going to be generate a raster mask because we're going to give area imagery, and it's going to run the model because it's all raster mask. It's going to generate vector data directly. Also, you can specify which model you're going to use. We're going to use this base model. So once you specify this, one line of code. Now we can run the reference. We're just going to call the object detection. So object detection, what you need is, okay, what imagery you want to do the detection, where do you want to save the output to, and the model, which model we use. So the model is the one that we got from the previous training steps. And you can also specify the window size, basically the chip size. So try to use the same as your training data, because earlier when we create the image chips, we use 512 and the overlap. So everything remains the same. You can specify the confidence space threshold, means the value going to range from 0 to 1. So the higher the confidence, the smaller number of objects you want to detect. The smaller, you might be able a lot of smaller value, you might end up with a lot of false positive. And the base size and also the number of channels. So these are pretty much the same when we use to create the image chips and also when we use to do the training. So make sure you use the same parameters. And like I said, if you train on 4 spectral bands, you use 4. If it's 3, you use 3. If it's 8, you use 8. Whatever number you like. So one line of code, and you can do the object detection. So take a look. It's going to basically subdivide your testing imagery into smaller tiles. So in this case, we have 65 windows. So basically 65 tiles. 512 by 512, and the nice thing about this is it automatically merges the result as a single geotiff. So in that way, you don't have to do the work by yourself. Again, if you're interested in learning the algorithm, you can go to the website here, and then there should be the algorithm source code, object detection, and from here you can look at the source code. Again, this one, it also calls on the other function, inference on geotiff. So you can check on the other one here, inference on geotiff. So this is the function. You can look at the source code. Again, these are a lot of lines of code to simplify the process to help you deal with the output from the training model. Okay, so once you have the raster mask, you are welcome to visualize the mask if you want, but I'm going to directly convert it to vector data. So using this function, orthogonalize function to, because it's building, so we want to basically regularize the building footprint so it looks nice. Otherwise, just raster mask, it doesn't look good. So it's going to be pixelated. Okay, so run it. It's going to show you the progress bar, how many buildings in there. For example, 941 in this imagery, and it's going to loop through that and then to change to vector data. And the final step, now we can visualize the result. Okay, so take a look. So we have this testing imagery. We also have the raster, the vector mask, and zoom in to take a look. Super nice. Some of those are just a rectangle, but you can also see some rich buildings. So the it aligns pretty much very well with the original with the testing imagery. You can turn the layer on and off. And like I said, there will be some missing buildings. It's perfectly normal. We didn't train the model for a long time, just 10 epochs, less than 1 minute. And also some small buildings. I also noticed the last building, this one is also not detected. It's probably because the window size. So if I increase maybe the window size from 512 to 1024, and it might be a little bit better. I haven't had time to test it, but at least I want to show you this is how quick it is, how powerful it is to train your own models. And all you need is just some footprint, and you can use to detect any object. It doesn't have to be buildings. You can detect trees as well. You can detect roads. You can detect anything. You can detect cars. As long as you have the training label, you have the satellite imagery, aerial imagery, and have some labels, vector data format or raster format, either one is fine. Now, then with couple minutes, you will have your results. And you don't need to know all the technical details about deep learning architecture. All you need is just pick up the one from GeoAI, and we simplify all the process for you. The last step I want to show you is a split map. So you can also just you have a slider, so just passing the left layer would be the vector, the polygon, and on the right we're going to show you the basically the testing imagery, and you can specify the style. For example, I want it to be red color, and also fill opacity just 20%. Also have the base map align at the bottom of the data. So this is what I show you at the very beginning, and super nice. You can apply the run the inference on a large imagery. It doesn't matter because it's going to subdivide your imagery into smaller pieces and then just run the inference. So it's not run the inference on the whole imagery all at once. So you don't really necessarily need a large GPU to do that. You can run it on a consumer grade GPU. 6 GB, 8 GB, it should be fine. As long as you can have the pre-trained model. So you can also use other example that I provide in the tutorial series, but this looks really nice, and just a simple mass eye CNN detection model, and then you can spend just a couple minutes. You can adapt this one to your own area. And I haven't tested in other imagery yet, for example, Sentinel, Landsat, and other imagery, but at least it works very well on this high resolution aerial imagery. And you're welcome to try it out and let me know what result do you get, or if there's any room for improvement, feel free to leave your comments down below. So this is just the first of the training deep learning model series. There will be more coming. For example, train image classification model, use lane cover, or maybe training change detection model. Use input. You can have multiple images before and after, and then you have some vector data set. So I will be building the packages, adding more functionality that makes it really easy for you to train your own model or use any pre-trained model to do deep learning and to get some useful information from geospatial data. Okay, so that's all for this tutorial, and I hope you find it useful. I encourage you to try it out with your own data and let me know your comments below. What do you think? And if there's any suggestion for improvement, happy to hear that. That's all. Thank you for watching. I will see you in the next one.